We are at page 2. So this first question is asking about the spring in your clicky pen. It has a spring constant of 2 newtons per meter. That's something to note. And it's stretched 0.02 meters. These are probably important numbers, right? So when it asks what force will we pull it back with, we have to go look at our equations, right? Look at our equations page and find the equation that has what we're looking for. It says that we need the force, and we've got a spring constant and a stretch. Oh, what do you know? Here it is right here. So then it's just a simple matter of writing down our equation and then filling it in. Equals a spring constant of 2 and stretch of 0.02, and so we get 0.04, which would be, it's a force, so it's measured in newtons, right? Simple as that. For B, we've got what type of energy will the band have when it's stretched? Again, you need to look at your equations page. This equation sheet is going to be important the whole test. You got to keep referring back to it. So here's where we have an energy equation for this, and we can just write that down. I always want you to be in the habit of writing it down first and then solving it. So equals 1/2 times 2 times 0.02 squared, which 0.02 squared is going to be 0.004, and then half times 2 is 1. So energy is 0.0004. What's our unit for energy? Joules. I'll go ahead and write that out, but usually you just have to put the J. Right, and this is newtons. So for C, how much of that energy will the band have? Oh, what type of energy? Oh, that's right. I went a little bit ahead of myself. It's elastic, which is elastic potential energy. And then, of course, I solved C just now. Just real kind of interesting, I kind of put how a pen works here. A small video here. Basically, when you push the button, there's a little thing that like latches in if you look at the inside of like a clear pen. And so the spring kind of holds it together, and then when you click again, it retracts. And like that little thing releases. So that's how a pen works. So for number 6, if a box of hoverboards with a mass of 300 kilograms lifts you to a height of 5 meters, again, I want you to kind of note variables as you go through, right? These things are probably important. What type of energy will the mass have at this height? So these look like complicated 3-part questions, and I want you to work ahead of me, remember? I don't want you just counting on my video to tell you all of the answers. Some of these answers are really easy. What type of energy will a mass have if it's at a height? Of course, it will have gravitational potential energy. That's the energy that comes from being a height. How much energy? Well, let's see. We look at our equations page as we always do. We've got Eg equals mgh, and we can just fill that in. Equals mass of 300, g is 10, height is 5. We get a pretty simple 6,000 joules of energy. You've got to have those units. That's the only way I can be upset with you. And I'm sorry, it's not 6,000. It's 15,000 joules of energy. You've got to have that unit, or I'm going to be counting off. It's just, you got to have it. And what will happen to that energy when I drop the box? So here we've got a little bit more of a short answer question. And I don't know, I got this little video of somebody dropping an iPhone, right? So when we drop something from a height, its gravitational potential energy, oh, no, I don't know why it's in equation mode, will turn into kinetic energy, right? Transform actually is an even better word than turn into. That's our physics word, right? We want to use as many physics words as possible in our definition, in our explanations. So gravitational energy will transform into kinetic energy. That's all you need to know. That's all. So pause the video, try to do this next one without my help, and then use this video to come back and get the answer. Alright, so when the race starts, you accelerate during the first 5 meters using a force of 200 newtons. Again, we want to note these things. They're probably going to come up. So how much work do you do during this time? All right, so A has to do with work. And so let's go, right? You're going to get tired of me saying this. Let's go look at our equation sheet. Where's our work? Oh, work equals force times distance. We've got that right there. So work equals force times distance, so equals 200 times 5, right? Easy, pretty easy. 1,000. What's the units of work, though? Well, work gives something energy. In fact, work is energy. Work is how much energy we transfer to something. That's even on your equations page. I was extra nice giving you that one. So, it's 1,000 joules of work. And so what kind of energy do you have now? Now that we've accelerated and we've started running? Kinetic energy, right? Kinetic energy is the energy of motion. And how much of it? Well, kinetic energy equals, I know you're going to get sick of it, the equations page, right? EK is 1/2 mv squared. So we can go from there. We've got 1/2 times, what's our mass? Uh-oh. Well, I told it to you later in the equation, right? It's 50 kilograms. And what's our velocity? Well, we don't know it. Because this isn't how we solve for the kinetic energy this time. It's very common to like go to the equation and then be like, wait, I don't have that information. So how else can we find out what kind of energy we have? Let's see, what else tells us the energy? How about the work? Work is energy, so we have 1,000 joules of energy. We have to, because that's how much work we did, and that's how much kinetic energy we have. So specifically, 1,000 joules of kinetic energy. See how I worked through that? I really wanted to show you that that kind of getting it wrong and then correcting myself. All right, so how much work do we do for the next 95 meters of the race when we're going at constant speed? The crucial part here is that it's not, if we're going at constant speed, we have no change in energy. Even though, obviously, it takes effort to run, if we're going at constant speed, we haven't changed our energy. And if we haven't changed our energy, what's happened? Well, how much work have we done? We haven't done any work. If there's no change in energy, you haven't done work. So this page is maybe easier than you thought, right? I really do want you to work ahead. And maybe try this STEM section here. The STEM question asks, how fast are we going? Now we're going to use that kinetic energy formula at 1/2 mv squared. But this time, it's not going to be what you're used to. This is why I want you to write the whole equation. Whenever I give you something like this, I want you to write the whole equation because EK equals 1/2 mv squared, but we don't know V. We're trying to find V. How fast are you going? Do we know EK though? Yes, that's what we set up here. If we did 1,000 joules of work, we have 1,000 joules of kinetic energy. That connection may seem obvious when I say it, but for you to make it is going to take an extra leap, and that's what I want you to be able to do. So we have 1,000 equals 1/2 times the mass of 50 times velocity squared. And so now we've got an algebra. 1/2 of 50, we replace this is 25, right? And then to get V by itself, we need to divide both sides by 25, right? And then we've got V squared. Let's see if I can insert equation. Then we've got V squared equals 1,000 divided by 25. And 1,000 divided by 25 is, of course, 40. And the square root of 40, right? Because now we've got to square root both sides to get V all by itself. So we get V equals 6.32. What are our units? What are our units? We've got, it's hard to say, right? This is measured in joules, mass is measured in kilograms. You just have to remember all of our velocity units all year have been in meters per second. All right, so moving forward, this number 8, a cheap but reliable Honda, mass of 1,500 kilograms, is moving at 40 meters per second on flat ground. What kind of energy does the car have as it speeds? So as you go, as you're moving, what kind of energy is that? Again, work ahead of me, pause this video, come back. Kinetic energy. And for B, how much of that energy? Well, we're going to go grab our equation, right? EK equals 1/2 mv squared. We're going to start plugging things in. Equals 1/2 times what's our mass, 1500, times the velocity, squared. I don't know what 1,200,000 joules, which is a lot, but cars have a lot of energy, right? So C, what if the driver takes your foot off the gas, what's going to happen to that energy? So the total energy is going to go down? No, never, right? Total energy is going to stay the same as it always does. But friction is going to create some heat energy. So the car is going to slow down, that reduces the kinetic energy. The kinetic energy transforms into heat energy. And so that kinetic energy is the energy of motion, so when there's less of that, there's less motion. Alright, so when we're bouncing on a trampoline, mass of 50 kilograms that stretches 2 meters downward, these are probably important pieces of information, right? And the spring constant is 800. So what kind of energy do we have at the bottom of the bounce when this is stretched 2 meters downward? Well, if there's stretch, we have elastic potential energy. And how much of that energy do we have? Well, as usual, we have to look at our equations page and find the one that has our spring constant, and they gave us mass, and then there was also this stretch of 2 meters. Spring constant and stretch are both here in the elastic equation. So we get that, and we can plug it in, equals 1/2 times 800 times 2 squared, which is going to be 1600 joules of energy. Now the tricky part. How high up will we go? So let's look at equations first. I love looking at equations and thinking of them there. We've got one equation that has height in it, Eg equals mgh. And so if we just write that down, maybe we'll be able to figure out what to do with it. If we start plugging things in, we've got Eg equals mass of 50, okay, and we know G is 10, but we're looking for H. So when we see a formula with two variables in it, we need to know one of those variables to figure out the other one. We're trying to figure out how high. So how much Eg do we have at the top of the jump? Well, if we had this much energy at the bottom of the jump, right, the energy at the bottom is the same as the energy at the top, and now it's gravitational potential when we go up into the air, when we're bounced up into the air. So this 1600 just goes right here. And then we can just simply, 5 times 10 is 500, divide both sides by 500, and we get a height of 3.2 meters. And that's how high up we go. I got a quick example of two kids who are too high up. They're jumping off of their roof onto a trampoline, which is going to give them extra gravitational potential energy, right? And that's going to translate into more elastic potential energy. And then they got the little double bounce situation, and into the bush he goes. Fun stuff. If we look at this next question, after one of our bounces while in the air, someone removes the trampoline. Explain using the words conservation of energy and transformation what's happening from the bounce to the air and back to the ground. So let's start with the bounce. When we bounce, we are harnessing what? Elastic potential energy, right? And when we go back up, that elastic energy transforms into, I've already used transformation, right? Transforms into kinetic energy, which then transforms into gravitational energy. The total energy remains the same the whole time because of the law of conservation of energy. So how fast will we be going when we get to the ground? We've got a mass of 50 kilograms. Okay, so which of our equations has the velocity in it, right? Because we don't know how fast. Right here, EK equals 1/2 mv squared. So let's check out that equation and see if we can figure out how fast we're going. We need to plug in the other variables. We need to plug in what we know. And we just said that the transformation from elastic goes to kinetic and then back to potential. So then when we go back to the ground, as we fall back, the GPE turns back into kinetic. And with no trampoline to catch us down at the bottom, we are going to have kinetic all the way down. So this 1600 joules of energy that we had up here with the elastic and that we had up here with the gravitational is also the EK that we have down here. So 1600 equals 1/2 times 50 times v squared. Where did I get 50? It says we have a mass of 50 kilograms. So this is just algebra. Algebra from here. So 1/2 times 50 is 25, right? And then we just have to divide both sides by 25 to get v by itself, right? To get v squared by itself. So divided by 25, 1600 divided by 25 is 64 equals v squared. And then to get v by itself, we square root both sides, and v equals 8 meters per second.